The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
So this week we are going to talk about counting. Tonight is problem set 8 due. For this week we will post a new problem set tonight as well. Counting is very important. The rest of the semester after this week we will actually explain probability theory, and that's all based on counting. So we're going to teach you this week a whole toolkit of all kinds of ways how to count, and as you can see we're going to talk about a lot of different kinds of rules. A mapping rule we talk about, a principle, Pigeonhole principle, another rule, a product rule and a sum rule. And these are all ways to count one thing by counting another thing. Actually what we are going to talk about is how to count, say, a difficult set of objects, and then we will map those objects to something that we can count in a much easier way. Okay, so let's start with a lot of definitions actually. So we have to talk about sets, sequences and permutations to start off with. So the definition of a set is as follows. A set is actually an unordered collection of distinct elements. So as an example, we may have, say, a set that contains the items, the elements A, B, and C. Well, if we reorder these elements, it doesn't really matter. It's still the same set. We can also write it as, say, the set C, A, B. On the other hand, if we have a collection in which, say, the element A appears twice, well, these two are not distinct, so this is not a set. So this is not a set, but it is a collection, and you may call this a multiset, but we'll not go into that. So we will be talking about sets, and we are interested usually in the cardinality of a set. So what's that? The cardinality or size is defined as follows. It's just cardinality, it's just a number of elements that the set S really has. So that's the number of elements in S. And how do we denote this? This is denoted by two vertical bars around the letter that represents the set. So we denote this as follows. Now, when we talk about sets, we may also be interested in ordered collections of elements, and that's what we call a sequence. So a sequence is defined as follows. A sequence is an ordered collection of elements, and we also call these elements components or terms. And these elements do not necessarily have to be distinct, so not necessarily distinct. Now, as an example, so how do we denote this? For sets, we use this type of notation, like this symbol. For sequences, we just have a very simple type of bracket, just the round bracket. So an example could be, well, the elements A, B, and C. The first entry or the first term of a sequence, depending on whether you look at it from the left or the right, that may differ, is here A, B, and then C. Another one could be A, B, and A. And as you can see, the element A occurs twice in this sequence. So we're going to relate sets and sequences. And let's talk about the permutation. So a permutation of a set is defined as follows. A permutation of a set S is actually a sequence that contains every element in S exactly once. So every element in S occurs exactly once. And as an example, we may look at the set that we have described over here, the set A, B, and C. And, well, how many permutations are there? So, first one, I may just order the elements in A, B, and C. So I have, say, the sequence A, and then B, and then C. There are many more. I can, for example, start with B, and then C, and I may cycle through to A. That's another permutation of these three elements. And I can do that once more. I can, for example, start with C, and then A, and then B. And it turns out that we can do a few more. We can also start with C, and then B, and then A. We sort of reversed the order that we had over here into its opposite. So first C, then B, then A. And we can look at their cycle, their shifts. We start with B, A, and then we rotate through to C, which is what we did over here when we went from this permutation to this one. So we have B, A, and then C. And then we may start with A, and we have A, C, and B. It turns out that this is actually all the possible permutations of this set. So there are 6 of these. And in general, how many permutations are there of a set of n elements? So let's have a look here, what we did. So if I want to create a permutation of a set, I may start off by selecting for the first term A, B, or C. So I have actually 3 choices. So for the first term has 3 choices. For the second term over here, well, for example, suppose my first term was B, then the second term, well, must be an element that is different from B, is yet part of S. So I have only 2 choices for the second term, either C or A. So the second term has 2 choices. And once I've chosen the second one, well, if I've already chosen B and C, there's only one element left in the set over here, only A, so I have only one choice left. So in this way, we may count the total number of permutations of this set as the number of choices I have for the first term, times the number of choices for the second term, 3 times 2, times the number of choices for the third term, which is only 1. So the third term has only 1 choice. Now, in general, we can do this for any permutation, and if you want to count the number of permutations of a set with n elements, well, it turns out that that is equal to n times n minus 1, just like here. We have 3 elements, 3 times 3 minus 1, and so on. N times n minus 1 times n minus 2, etc. And all the way up to 1, and this is n factorial. And you've seen this already when we talked about Stirling's formula and how to approximate this. Now, this type of reasoning we will generalize later on when we come to the generalized product rule. But this is already a first example of how we go about this. So permutations relate sets and sequences. So now we go on to define more special functions. So permutation is one kind of mapping. So let's now define functions. And then we will talk about a few different flavors of those. We talk about surjective functions, injective functions, and bijective functions. And the whole idea is that if I can use a mapping from one set to another set that satisfies some of those properties, I can say something about how their cardinalities are related. And that's what we want. We want to count. Okay, so the definition of a function is as follows. So a function f from x to y is actually a relation between the sets x and y. And we say that, with the property that every single element, of x is actually related to exactly one element of y. And we will call x to be the domain of the function f, and y we will call the range or image of the function f. So let's give an example and see a couple of examples first of all, of a function, and then relations that are actually not functions. So suppose we have a mapping from x, which just contains the elements a, b, and c, just in line with this example over here. And we have a mapping f that maps to the set y, and the y is just the numbers 1, 2, and 3. Well, I could map, for example, a to 1, b to 3, and c to 3. Now, this is a function because every element of x is mapped to exactly one element of y. A is just mapped to 1. B is also mapped to an element, only 3. C is mapped to 3 as well. And we usually write this as f evaluated in A is equal to 1, and fb is equal to 3, and f of c is equal to 3 as well. Now, what is not a function? Well, I could, for example, add another edge over here if I wanted to. Well, this is not a function because b is now mapped to two elements, 2 and 3, and that's not what's covered by this definition. So this is not a function. I could also remove, say, an edge. Well, in this case, b is not mapped to anything at all, and that's not a function either. So we really have the property for functions that there is exactly one outgoing arrow, if you want to think about it as being a graph, from each element in x to exactly one element in y. So now we can talk about a few definitions. So we will talk about these few properties, surjective, injective, and bijective, and then we can start to do a few interesting examples. So a function f that goes from x to y is called surjective if every single element, if every single element of y is mapped to at least one, is mapped to at least once. So what does that mean? To at least once. So every element of y So say 1, for example, here, is mapped to at least once. Well, to 1, the element 1, we have mapped A, so that's great. But for example, the element 2 is not mapped to at all. So this particular example is not surjective, but we will come to a few examples that are. So here we have the distinction that every element of Y, so every single element of Y, is mapped to at least once. Then injective is defined in a similar fashion. But now every element of Y is not mapped to at least once, but at most once. So let's have a look over here. And that's also not true for this example, actually, because 3 is mapped to 2 times, so it's not mapped to at most once. So this example is also not injective. Because if a function is injective, then every element of Y of the range is mapped to at most once. Bijective is if we have that every element of Y is mapped to exactly once. And we can see that a function is bijective if and only if it is both surjective and injective. So bijective if and only if we have both the properties surjective as well as injective. So let's give a couple of examples. So as a first example, we may have the set X and Y. We have 1, 2, and 3, and say the 2 elements A and B over here. 1 is mapped to A, 2 is mapped to A, and 3 is mapped to B. And now we can see that every element in Y is mapped to at least once. This one is mapped to 2 times, this one is mapped to once. So this one is actually surjective. So that's great. Another example of something that is injective is if we have, say, 1, 2, and 3, and A, B, C, and D. 1 is mapped, say, to A, 2 to B, 3 to D. Well, in this case, we have that it is injective because every element of Y is mapped to at most once. Once, 0 times, and once. So this one is injective. And this one is not injective, right? Because this one is mapped to 2 times. This one is not surjective, but because this one is not covered at all, it's only mapped to once. Okay, so let us talk again about permutations. So when we talked about permutations, we can define a mapping using a permutation. That is an example of a bijection. So let's do that. And then we can come to the mapping rule. And we can start to do some counting. So for example, if we have a permutation, A1 up to AN, of, so let this be a permutation, of the set S that contains all the elements A1 up to AN. So this is just one example of a permutation. And now we may define the following function. We say that pi evaluated in AI gives us output I. Actually, what we mean here is that if we take an element in S, then this one is mapped to, under this function, to I, if and only if A is in the ith position in this permutation. So if and only if A is in the ith term in the permutation. So in this case, we know that pi is bijective. And why is this? Well, we know from the definition of a permutation that in a permutation this is a sequence in which every element of S occurs exactly once. So that means that every position is covered exactly once by an element of S. And that is exactly the definition over here, which says that every element in the range is covered exactly once, is mapped to exactly once by an element in the domain. So this is an example of a bijection. Okay, so now that we have defined functions and the special properties, let's talk about the mapping rule, which we will do over here. And now, for the first time, we start to talk about the cardinalities of sets and how they're related to one another. So the mapping rule is that, first of all, if f is a function from x to y, and if f is actually surjective, well, what do we know? We actually know that the cardinality of the number of elements in the domain is at least the number of elements in the range. And why is that? If you look at the definition of surjectivity, well, we know that every element of y is covered by some element in x at least once, and all the elements in x are mapped to exactly one element in y. So we know that the cardinality of x is at least y, because every element in y is mapped by some unique, distinct element in x. And if a function f is injective, well, in that case, we know that the reverse relation holds, so inequality holds. The cardinality of x is at most the cardinality of y. So why is that? Well, every element in an injective function, right? Every element is mapped to at most one element so every element in y is mapped to by at most one element in x. So we know that all the elements in x are mapped to some element in y, but every element in y cannot map to by more than two times by something in the domain. So we know that this inequality holds. Okay, for a bijective function, we have that both these properties hold, and we will have an equality over here. So, oops, if this one is bijective, we have that the cardinalities are equal to one another. And this is also called the bijection rule. So let's give an example where we want to find out how many ways there are to select 12 donuts from 5 varieties. So let's see how that would work. And the whole idea is that we're going to define the set that we want to count, which is all these possible configurations of donuts over 5 varieties of flavors. And then we're going to map these to another structure that we can understand a little bit better. So let's do this. So as an example, let x be all the ways to select, say, 12 donuts from 5 varieties. So let's give an example. For example, we may have 2 donuts, and they are in the chocolate favored basket. So we have chocolate. And suppose we have no donuts in the lemon-filled version of a donut. Suppose we have a whole bunch of donuts, say 6 of those, that are with sugar. We have some that are glazed, say 2. And finally, we have just a couple of plain donuts. So this would be a configuration that is in X, because we have 1, 2, 3, 4, 5 varieties. And we have 12 donuts 2 over here, 6 here, 2 and another 2, 12 donuts that are selected from these 5 varieties. Now, if we are going to try to represent such a configuration, that's usually how we think about counting, then we may map this to a 0-1 sequence. So how do we do this? We can just map the donuts to zeros, the divider between the 2 baskets as a 1. So this is a 1. Then we have no zeros between these 2 ones because there are no donuts in the lemon-filled basket. So we have a 1 that is the mapping from this divider over here. We got 6 zeros. We have another 1, that is this divider. 2 zeros, 2 donuts in the glazed version, and so on. So what do we see here? We have a 0-1 sequence where we have 12 zeros and we have 1, 2, 3, 4 ones. And we can see that this mapping is actually bijective, because if I have 2 zeros, I can map them back to donuts. The divider I can map, the one I can map back to the divider between 2 baskets. So let Y be the set of 12, all kinds of configurations of 12, all kinds of sequences. Oops, maybe I will not take this one out. Let's do this one. So if we are going to define Y as the set of all 16-bit sequences with exactly 4 ones, then we know that by the bijection rule, we have created this bijection over here, that the cardinalities of x and y are exactly equal. So now we know that by the bijection rule, we have been able to count the number of elements in X by counting something else, which is really how we proceed in these types of proofs. So if now we are now able to just count these types of objects, and later on, next lecture, we will actually figure out the formula for this one. So this is an example of how we can use the bijection rule. Now another example is one in which we are going to count subsets. So I'll give a lot of examples through these 2 lectures. And also the problem set, as you will see, will have a lot of small little parts with all kinds of countings that you will need to do, applying different rules. So let's talk about how to count subsets of a set X. So what we want is a bijection from subsets of a set X containing of, say, 1 up to n, so the integers 1 up to n, to n-bit sequences. We know that we can do this if we define a bijection as follows. So we map a subset S under a mapping F to a bit sequence B1, B2, all the way to Bn via the following relation. Bi is computed as either a 1 or a 0. It's computed as a 1 if I is in S, and it's a 0 if I is not in S. Now we know that this is a bijection. So if we have a bit sequence, then we can construct from this mapping the corresponding subset. If you have a subset, we can use this mapping to construct the corresponding sequence, the corresponding bit sequence. So let's so how many n-bit sequences are there? Well, there are 2 to the power n n-bit sequences. Why is that? Well, we have two choices for B1, a 0 or a 1, two choices for B2, 0 or a 1, and so on. So we have 2 times 2 times 2 choices over here. So we have 2 to the power n choices for the number for a bit sequence. So there are 2 to the power n number of bit sequences. And this is actually equal, because of this bijection rule that we have described over here, this is equal to the total number of possible ways to select subsets of X. So this is the number of subsets of an n-element set. So this is a very nice way to demonstrate how we can use the bijection rule to count something that appears to be much more harder to think about, to grasp. At least for me it's harder to grasp. So I have a subset that can be any size in a set of n elements. And now I can find this really easygoing mapping that I can show to be bijective, and all of a sudden I know how to count it, because I can just look at the image and count those types of objects, in this case n-bit sequences. I get a really easygoing number that I can compute fairly easily, and now I have counted something much more complex. So this is how we generally will think about these things. Okay, so let's talk now about the generalized pigeonhole principle. So we have covered quite a lot of definitions right now. So we explained the functions, mapping rules, and now we come to the generalized pigeonhole principle and a few other rules. Okay. So what about the generalized pigeonhole principle? This is actually the following counting argument. If I know that the cardinality of a set X is more than k times the cardinality of a set Y, what do I know? Well, I know that for all functions f that have domain X and range Y, I know that there must exist k plus 1 different elements of X that are mapped to the same element in Y. And if we take a specific case, k equals 1, we will actually call this the pigeonhole principle. And let me just demonstrate it by the famous example of the pigeons. So, well, if I have more pigeons than the number of holes than they can fly into, I know for sure that there exists a hole that 2 pigeons will visit. So that's where the name comes from. So let me write it out. So an example is, if I have more than n pigeons, so the pigeons form the set X, and say they fly into n holes, and the holes is my set Y, well, then I know that the cardinality of X is more than the cardinality of Y. I have more pigeons than there are holes. So I know that at least 2 pigeons will fly into the same hole. So for the generalized case, well, how can we prove something like that? Well, we could use, for example, something like a contradiction. For example, suppose that, for all k plus 1, suppose that the negation is true, so we assume, so how do we prove this usually? So assume we have this. We want to prove this. Well, suppose that's not true. So suppose there's a mapping F such that for all k plus 1 different elements of X, they are not mapped to the same elements in Y. Well, what I really know then is that every element in Y is mapped to, at most, by k distinct elements of X. So that means that the total number of elements of X must be at most k times Y. And that's not true. It's larger by assumption. So I have a contradiction. So this is a very general principle, though. And it's worth writing it all out, because this is a famous a rule that we will use in counting, and it leads to interesting results. Okay, so let's give another example. Let's think about Boston. In Boston, we have, say, 500,000 non-bald people. It turns out that there are at least 3 people that have the exact same number of hairs on their head. That's kind of weird. How do we know that? I cannot point out any 3 in Boston that have the same number of hairs. I have no idea, but somehow I can count and use this principle and tell you that it must be true that in Boston, with 500,000 people, there are 3 of them that are not bald, so we exclude the bald people because that would be easy, they all have 0 hairs, but say non-bald people, that actually have the same number of hairs. So how do we do that? How can we make such types of conclusion? So say Boston has about 500,000 non-bald people. And let's call this set X, because we're going to use the pigeonhole principle. So our claim is that there exists 3 people in Boston such that they have the same number of hairs on their head. So how do we do this? Well, we know that we may generally assume that any person has at most 200,000 hairs on their head. So the number of hairs on a head is at most 200,000. So how should I define my set Y in order to apply this pigeonhole principle? So what do I do? So I want to have a mapping, right, from all the people, the set X, to their number of hairs. So the number of hairs on one's head is going to be the set Y. And what do we know? We know that the cardinality of Y is 200, at most 200,000. Actually, the way we defined it, it's exactly 200,000. And the set X has a cardinality of about 500,000. So what do we know? We can apply our generalized pigeonhole principle. It's very surprising because we notice that X is more than 2 times the cardinality of Y. 2 times 200,000 is less than 500,000. So I know that by this particular principle, this particular mapping must have the property, because this holds for all mappings, that there are at least k plus 1, 2 plus 1, 3 different people, 3 different people in Boston out of this set X that are mapped to the same element in Y. That means that they have the same number of hairs on their head. So this is kind of really surprising. We can make a statement without really inspecting every single person's head, but we can still make a statement about about the fact that there are 3 different people in Boston that have the exact same number of hairs. So this is an example of a non-constructive proof, and I will give another one. And it's a very important principle. Actually, it's a new technique that you haven't seen before. So far, we have been constructively proving all kinds of properties using induction, mainly. And this is what is called a non-constructive proof, because I cannot give a specific example that demonstrates that this claim is true. But yet I've shown that it is true, but in a non-constructive way, without an example. Okay, so what about another one? For example, we may pick 10 arbitrary 2-digit numbers. So pick 10 arbitrary double-digit numbers. And, well, we can pick any sequence of numbers. I'm just picking a few. You may add a few too. I don't know, 2, 7, 14, I don't know, 31, 25, 60, 92, and so on. So I have 1, 2, 3, 4, 5, 6, 7, 8, I don't know, 9, 9, and another one, say 91 or something like that. So I have 10 double-digit numbers. It turns out that I can show to you that there are 2 subsets that if I look at the sum of their elements, so I look at the sum of the elements of the first subset, and I look at the sum of the elements of the second subset, that I can find 2 subsets that have an equal sum. Now, if you just look at those numbers, and I've now picked like 10 arbitrary double-digit numbers, well, usually it's pretty hard to figure out whether that's really true or not. Maybe I have been selecting the numbers in such a way that it's easy to see. I mean, we can still try to wrap our minds around it and try to really solve this constructively by giving an example. It turns out that we can prove this statement, and we will use the pigeonhole principle. And we do not even have to actually... Oh, you have a question? Oh, sure, we can make it double digits. So I can put a 0 before 2 if I want to. But yeah, just select something else. It doesn't really matter. So what we're going to show now is that through the pigeonhole principle, we can prove that there are 2 subsets that have the same sum. And just by inspection, it's a very hard problem to solve. So I do not even give you an example, but we can still show this. So how can we go ahead with this? So let's think together about this problem. So I want to choose 2 sets, x and y, and somehow I want to have a mapping, right? I want to have a mapping from any double-digit set of numbers. Somehow I want to map that to sums, because that's what I'm interested in. I'm interested in sums. And I want to show something about how hard it is, or I want to show something about subsets of these double-digit numbers. So what do? I take x as the collection of subsets of these numbers. And I want to show that there are at least 2 subsets that map to the same sum. So let's first count how many we have here. We already did this. We made a mapping from subsets to binary sequences, bit sequences. And in this case, we have 10 numbers. So we have 2 to the power 10 possible subsets. So this is equal to 1024. Now y is going to be the sum of a subset. So what do I know? I note that the possible sums range from 0 all the way to, well, what's the maximum sum that I can have out of 10 double-digit, a subset of 10 double-digit numbers. So I can select all the 10 elements in this set. And they are double digits, so at most they are 99. So I know that this set is really the set of all possible sums. Now we know that 1024 is more than 990, so the cardinality of x is more than cardinality of y. So by the pigeonhole principle, we know that there exist at least two different elements of x. In our case, there exist two different subsets that map to the same sum, the same element in y, the same sum. So now we have shown that even though we have not shown any particular example that demonstrates this claim that there are two different subsets that have the same sum, we still got a proof using counting that this is true. So this is called a non-constructive proof. Let me write it down. And this is a great way of proving properties. Okay, so now we can continue with another definition, where we look at another property. Over here we talked about surjectivity, injectivity, and bijectivity. And now we will talk about the following property. We say that a k to 1 mapping, k to 1 function, is f from x to y, actually maps exactly k elements to of x to every element of y. So what do we know? Well, we can have the following counting rule that we call the division rule. And it says that if f is such a type of function, so if f is k to 1, well then we know that the cardinality of the domain is equal to k times the cardinality of y. And why is that? Well, exactly k elements of x map to each element of y. So we have the first element of y, we have k elements of x that map to it. The second element of y, k elements map to that one. So we know that the domain is exactly k times the range, k times the size of the range. Now this division rule actually generalizes the bijection rule, which I've put over there, the bijection rule. And why is that? Well, that's because a function is a bijection if and only if it is actually 1 to 1. So if you replace k by 1, we have that exactly one element of x is mapped to every element in y, and that's the definition of a bijection. And the bijection rule says that if you have a bijection, then the cardinality of the domain is equal to the cardinality of the range, so for k equals 1 here. So let's give an example on how this works. I think we can take this out, actually. So let's give an example using a chessboard where we have two identical rooks, and we want to count the number of ways we can put them on the chessboard in such a way that the two rooks cannot see one another, meaning that the rooks are on different rows and on different columns. So let's give an example. So the example is like this. So how many ways do we have to place two identical rooks on a chessboard in such a way that no row or column is shared? So how can we do this? For example, let's look at a chessboard. And suppose we have a rook over here and a rook over here. And say the first rook is on row 1 and on column 1. And the second rook is on row 2, R2, on row R2, and on the column that is indexed by C2. So how can we describe such configurations? Well, I could describe this by using a sequence in which I look at the placement of the first rook and then describe the placement of the second rook. So I may have R1, C1, and then R2 and C2. So this could be a way to describe the positioning of these rooks. And I could create a mapping, F, that is doing this for me. And so if I call this an example of a valid, so let Y be the set of valid rook configurations, and this is one example of it. So this is part of this set. And if I define X as all the sequences R1, C1, R2, and C2, such that, well, the rook over here does not share a row with the rook that is described by this position, so R1 is not equal to R2, and they also do not share a column, so the rook, the first rook has column C1, the second one is on column C2, so also C1 and C2 should be different. So these sequences are really placements, right? So this describes rook 1, this describes rook 2, and the whole combination is really a placement. So now I have described a function f that maps a sequence that describes the position of the first and the second rook, maps such a sequence to an element in Y, which is a valid rook configuration. So now let's have a look at how we can apply the division rule. So is this function bijective? Is that true? So, so is it true that so I have a mapping that goes from here to here, but is it true that every valid rook configuration is mapped to exactly once? Is that true? Is this the only representation that I can use to, the only sequence that will map using this function f into a valid configuration? Yep, that's true. So you can switch rook 1 and rook 2, and it will still look the same. The two rooks are identical. They look exactly the same. So we have again, the exact same configuration, and we can see that this particular sequence also maps to the same. We just swap the positions, so we have R2, C2, R1, and C1, also maps under F to that same configuration. And it's exactly, those are the exact two possibilities that can happen to, that map to this configuration. Every valid configuration is mapped to exactly 2 times. So now we can use a division rule, because F is 2 to 1, so F is 2 to 1. What does that mean if you apply the division rule? It means that the cardinality of all those sequences is equal to 2 times the cardinality of all valid configurations, or in other words, the cardinality of all the valid configurations is the cardinality of all those possible sequences divided by 2. So now we can start counting x over here. So how do we do that? Well, we're going to use something similar as what we did when we were counting permutations, and I will generalize that in a moment. So how do we go about this? Well, let's have a look. If I have R1, C1, and R2 and C2, so this is a sequence. So how many choices do I have? Well, a chessboard has 8 rows, so I can choose 8 possible rows for the first rook. It also has 8 columns, so I have 8 possible choices for the column. But what about the second rook? Well, the second rook can be on any row except the one that I've already selected for the first. So that is 8 minus 1. We have 7 possible choices to select the row for the second rook. It must be different from the one that was already selected, and I have 7 possible choices. And similarly for this particular column as well, the column has to be different. So how many choices do I have? Well, it's not 8, it's 1 less, because I've already selected the one for the first rook. So I have 7 choices. So the cardinality of x is actually equal to 8 times 8 times 7 times 7. So it's 8 times 7 squared divided by 2. So now we have counted, by using the division rule, we saw that we have to divide this by 2. We have counted the total number of valid configurations. So now we are going to generalize this principle that we have talked about here. And we will do that over here, I think. Yeah. And that's the generalized product rule. So the generalized product rule is as follows. It's essentially saying that if we have a set of sequences of length k, then how can we count those? Well, if we know the following property, so let me first write out the generalized product rule is as follows. Let S be a set of length k sequences. Then I know that if there are n1 possible first entries, and if I know that once I've selected my first entry, there are n2 possible second entries, so there are n2 possible second entries for each first entry. And if I continue like this, so my choice for the third term in the sequence is always, I have always n3 possible choices given my selection for the first two entries. So if I have that property that continues in that way, so let me write it out. So we have n3 possible third entries for each combination, in this case, of first together with second entries. And if I continue this all the way to nk, so nk possible kth entries for each combination of all the previous entries. So then I know that the set S can be counted as, well, I have n1 possible choices for the first entry. Once I've chosen and fixed that one, I have n2 possible choices for the second, then n3 possible choices for the third, and I go all the way to nk. Now remember that, well, let's first talk about it from the perspective of the chess problem here. I got 8 possible choices for R1. Given R1, I don't care. I still have 8 possible choices for the column here. So I have 8 choices here. But for the third one, once I have selected R1 and C1, I only have 7 choices left for R2 and 7 choices left for C2. So that's an example where we use this particular generalized product rule. Also, when we were counting the number of permutations, we were saying we can fix the first entry of a permutation in n ways, if I have a permutation over n elements. And then I have the second entry, the second term of a permutation has only n-1 choices because I've already chosen one. Then the next one has n-3 choices because I've already selected 2 of them, so I have only n-2 choices left. Then I have n-3 choices because I've already selected 3, and so on. And I get n factorial. So that's the same kind of principle that we have here. So let me give an example where we can see how this works. So what do we do? In this example, we want to count the number of committees. So it's the exact same kind of principle that we're going to talk about. So we're going to count the number of committees described by a sequence x, y, z, where x, the first one, is, say, the leader of the committee. The second one indicates, say, the secretary. The third one is some consultant. So they're all different. They have all different roles. Such a committee is selected from n members. And in how many ways can I do this? Well, I have n ways to choose my first term in the sequence. I have n ways to choose the leader. So there's n ways to choose x. How many ways do I have to choose y? Well, if I've chosen already a leader, I need to choose someone else. So I have n-1 members left, n-1 ways to choose y. I'm just not allowed to choose x. And then I will have n-2 ways to choose z, except x and y. And so for each x, I have only n-1 ways to choose y. For each x and y, I have only n-2 ways to choose z. So if I multiply all this together, I get n times n-1 times n-2 to choose all these this is the total number of possible committees that I can select from an n-member set of people. So let's go to a little bit of a different example that uses the same principle. Okay, let's make some space. In this second problem, we're going to count, I will define to you a defective dollar bill. It's not really defective, but it's a property that we will assign to a dollar bill. So, and you can check for yourself whether you have one in your wallet. So let's define a defective dollar bill to have the property that if you look at the 8-bit serial number, it has the property that some of the digits appear more than once. So some digit appears more than once in the 8-bit serial number. So you can check your own wallet and check for your $1 bills and check whether you have a defective dollar. This seems to be pretty specific and rare property, right? Well, check your dollar, check your dollar bills. You'll figure out that you have probably a defective dollar bill in your wallet. So that's kind of weird. So this seems, this property, if you look at that, it seems to be something that is maybe a little bit more common than we thought it is. It seems to be so special. So let's do a counting argument and find out what's happening here. So let's look at a fraction of the non-defective. So we are counting the opposite of the non-defective bills. Well, that's the number of non-defective serial numbers. Divided by the total number of serial numbers. And let's call these small x and y, and count these. So let's see. So first of all, let's count y. Well, that's easy. I have 8 digits in my serial number, so I have 10 choices for the first digit, 10 choices for the second one, and so on. In total, I have 10 times 10 times 10, 10 to the power 8 choices. What about x? Well, I'm using, again, our generalized product rule over here. Well, if I'm going to have a non-defective dollar bill, then all the digits in the 8-digit serial number have to be different. So for the first digit, I have 10 choices. Now that I've selected my first digit, I have 9 digits for my second choice, for my second digit in the serial number. Then I have 8 possible choices, 7, because I've already selected 3 and I cannot choose those anymore, times 6, times 5, times 4, times 3. And now I have chosen an 8-digit serial number in which all the digits are different. Okay, so how many are these? Well, this is actually equal to 10 factorial divided by 2 factorial. And it turns out to be something like 1,814,400 possible choices. So now let's look at the fraction. It turns out that if you divide this by this, we get a really very small fraction. This is actually equal to 1.8144%. So a very small fraction is non-defective. So almost all the dollars are sort of defective. It simply means that they have the special property that some digit occurs more than once. So it's kind of interesting. So we can already see that by counting, it's sometimes a little bit counterintuitive, because if I would see this particular property, I would in first instance think that's a very special property, but that's not true. It's very common, it turns out. Now, a special case of the generalized product rule is the product rule. And this is defined as follows. We're going to first of all define a product over sets. The definition is that the product of a set A1 with A2 up to AN is actually equal to the set of sequences where each element, so the first entry, is selected from the first set. The second entry is selected from the second set, and so on. And now the product rule tells us, by just applying that reasoning over here, that the cardinality of the product of all those sets is actually equal to the cardinality of the first set multiplied by the cardinality of the second set, and so on, up to the cardinality of the last set. Because we have this number of choices for the very first element over here, this number of choices for the second one, and so on, and we apply that rule and we see that this is the result. Now, when we use this in specific to count all the n-bit sequences, we have exactly 2 choices for the first bit. We have the set 0, 1 in our example, times the set 0, 1 over here, and so on. And that's how we derived that we have 2 times 2, 2 to the power n choices for an n-bit sequence. So now we come to the sum rule, and we will give an example for that. So the sum rule states that if we look at sets, then we may be able to count their union. And we will consider a very specific case. In next lecture, we will talk about the general case. So the sum rule is the following counting mechanism. If the sets A1 up to AN are all disjoint, so they are disjoint sets, then we know that if I try to count the union of all those sets, it's going to be the sum of the separate cardinalities. So let me just write it out, actually. So it's the cardinality of A1 plus A2 all the way to AN. Why is this? Well, all the sets are disjoint, so there are no intersections between sets that contain elements. All the intersections are empty. So counting the union is really counting each separate set. And that's why we have this sum. And in next lecture, we will talk about the inclusion-exclusion rule. And then we will take into account that we have intersections that are non-empty. But let's give now an example where we talk about where we count the number of passwords with certain probability, with certain properties, and we will apply all these different rules together. And that's the type of problems that you would like to be able to solve. So in our example, in our last example here, we have that passwords have the following property. They are 6 to 8 symbols. So that's property 1. We have that the very first symbol must be special in the sense that it is a letter. And this can be an upper or lowercase. And say that the other symbols are actually letters or digits. So let's count the total number of possible passwords. We're going to use the sum rule. So let's define what kind of sets we are taking the symbols from. So the first set is for the first symbol, which we call F, of first. We have all the letters A, B, C in lowercase, and then all of them in uppercase. And in total, we have 52 elements in this set. For the second symbol, and or the other symbols, we have all these letters, but also all the digits, 0, 1, up to 9. And in this set actually has cardinality 62. We added 10 digits. So let's talk about actually we like to use this in the sum rule as well. So how do we count? What kind of possibilities do we really have? So let's describe the set of passwords explicitly in a formula. So let P be the set of passwords, of possible passwords. And this one is actually equal to, well, I need to choose a first symbol, and then I need to choose a second symbol, and a third, and a fourth, and a fifth, and a sixth. That's one possibility. I use 6 symbols. I can also use 7 or 8 symbols, but this is one of them. We also denote this as S to the power 5. That's an equivalent notation. The other possibilities for passwords are that we first choose an entry from F, a letter, and then we will need to choose another 6 symbols. In total, we have 7. And we have another possibility where we choose a first symbol, and then we choose 7 other symbols. So this has 8 symbols, this has in total 7, this one has in total 6 symbols. So this covers all the possible passwords. So let's count them. We know that these sets are all different, they are distinct. These are sequences that have 6 entries, 7 and 8 entries. So if we look at the cardinality of P, it's actually equal to the sum, by the sum rule that we just described over there, is equal to the very first one, F times S to the power 5, plus the cardinality of F, the product of F with S to the power 6. And we have F cross product, times S to the power 7. So this is by application of the sum rule. And now we can apply the product rule very simply, which is this one. So that's equal to the cardinality of F times the cardinality of S to the power 5. And then we have the same rule applied to this one. It's the cardinality of F times the cardinality of S to the power 6. And then we have the cardinality of F times the cardinality of S to the power 7. Now we simply plug in these numbers, and then you will have the total number of passwords that you can select from. It turns out to be about 1.8 times 10 to the power 14. So here we have applied both the sum rule and the product rule. So in general, you will see that you have to apply multiple rules together in order to find an answer to your counting problem. And you will see that on the problem set. And we will give a few more examples in next lecture. And we will start talking about the generalization of the sum rule called inclusion-exclusion. And we'll give you another type of proof technique called combinatorial proofs. All right, good luck with the problems.